Everybody can join. All right. So let's get started. Let me share the screen. Do you see my screen?
Yes.
Yes.
All right, thank you very much. So once again, good evening, everyone. Welcome to Dynamic Talks. My name is Milan Simakovic. I'm a senior big data engineer. And today, together with my colleague Masa and Luka, we are going to give two presentations. First presentation is related, is regarding data quality in big data. The second one is related on comparing two big data processing frameworks, Apache Spark and Apache Flink. If you have any questions, you can write them down into chat, and we can go briefly once the presentation is done. Okay, so let me start. Today, regarding data quality, today we are going to cover a couple of different things. First, we are going to try to emphasize what are the data quality problems in industry. We will show some examples. After that, we are going to try to define the data quality itself. And we are going to apply the data quality definition to a particular data set, so we can show how these data quality problems are resolved in production systems. And further on, we are going to discuss about some publicly available data quality tools. And last but not the least, we are going to go through the questions if there are any. I already used the chance to introduce myself, so I'll do it just briefly once again. My name is Milan Simakovic. I'm about 8 years in big data on various projects from on-premises to pure cloud. During this time, I had chance to work with different kind of big data frameworks, including some related to the data quality. So what is data quality? What is data quality itself, and why do we need it? So data quality should quantify the precision of our data. So what does it mean? Let us take a look on this quickly on this example. This example will emphasize that data quality issues can happen to everyone, to every company, and even to the biggest one. So one such blooper happened to the Amazon. Amazon celebrates the Prime Day, that is between 14 to 15 of June. And they had one very funny situation, for us funny, not for them, 2019 year, where when they decided to give some discounts and for particular, and they gave a discount for a particular Canon lens from 30,000 euros to 94 euros. So I didn't count how much percentage-wise this discount is, but we can see that it's really, really a lot. And this particular issue is related to data quality. So they needed one whole day to notice this error, and during this day they lost a lot of money. So the problem just was, as you can see, that someone reduced the price 100 times. One more example that is interesting is related to the healthcare. It happened somewhere in US. One man was going to the hospital for cystoscopy procedure. Unfortunately, at the same time, there was a name that had almost identical first name and last name like he is, and this patient was awaiting for Sersumption. Not sure how this is pronounced, and it happened that they switched one patient to another, and they gave to a patient a wrong surgery. So this is a very huge mistake, and big investigation is undertaken related to that. So this is only a few examples, and it happens all the time on all the places all over the industry. So from here you can see that almost every company admits that around 30% of the data that they have has the poor quality. So why? So how this poor quality is even possible? So there are. So this is a very complex, let's say, equation. So there are various different parameters that are impacting our data quality. The first impact is that nowadays the world and the technology and everything is very dynamic. So it directly reflects to the data. One very simple example is that, let's say we have one table and someone alters this table, but it's not propagated through all the systems, which brings a problem with data inconsistency, and hence leads to the poor data quality. There is also human error, and this human error can happen on multiple levels depending on where we are standing. So first level can be when someone mistypes something, let's say mistypes the name or email or maybe something third. And also it may happen on some higher level where some data engineers let's say forgets to clean up or to filter out, or does the outer join instead of inner join, etc., etc. So there are a lot of different possibilities that could happen that could lead to poor data quality. Of course, this almost all the 4 V's from the big data: volume, variety, veracity, and the fourth one can bring such problems. And of course, as one of the major impactor is also the technology. So technology is getting is evolving and getting more and more complex. Here we can see the data landscape for the current year, and the same picture reflects to different companies. The companies have more and more different tools that they use. They are synchronizing one between other, etc., etc. And all of this, on all of this complex system are leading to the poor data quality. So if we would able to somehow increase the data quality, we would be able to provide more precise information. We would be able to actually companies would be able to make more relevant business decisions, to provide a unified data framework or data definitions among all the systems, to minimize misunderstandings between different teams, and to ensure that only the valid data is collected, not junk. We can also show the data quality with these four hittings to the targets. On upper left target, you can see that there is the hittings are pretty wide. So this, and no one from the hittings are hitting the target. So such data set is both unreliable and unvalid. On the upper right corner, you can see that we also have a very high spread of the data, but some of them are hitting the target. So since it's wide, it's unreliable, but somehow it is valid because we sometimes hit the center of the target. In bottom left corner, you can see that the hits are grouped into one point, but they are not hitting the target. So we have a reliable data set, but invalid. And the bottom right shows both reliable and valid data set. So the companies are somewhere between first three targets, and the end goal is to make the data high quality as it is shown in the last target. So now we are going to go through some very simple data quality examples that will show a couple of different data quality issues. The first issue is related to the incompleteness. So on this table here, you can see two rows, and in these two rows we have a couple of different problems. First problem is that the first row, Michael, doesn't have the last name, the shipping address is null, and email is invalid, while the second line has some random string, has a default string for billing address, and shipping address is a null. The second data quality issue is related to data inaccuracy. So on this table here, you can see that for the first row, department is some junk value. On the second row, you can see that there is a typo. And on the third row, you can see that third and second column are switched. The third data quality issue is related to inconsistency. So here we have the table where we have different currencies on the last column. So here you can see on first we have dollars and the second one euros. So this is something that is that could bring the problems. The fourth data quality issue is related to invalidity. So what does it mean? So here we have everything populated, and it should be good from the syntax side. However, if we take a look on this table, it should show the products. And for the first row, we have available -10 shares. That is not something that is realistic. And the second problem is related to the retire date. So company is offering a bet even though they don't have it, they retired them. Fifth problem is related to redundancy. So this is something that happens quite often. So on this particular table, we have two users with the same email. And the last data quality issue is related to non-standardized values. For this particular example, the total column we have floats with two decimals and with 4 decimals. So based on this problem that are happening in on real life scenarios, we can define a definition. So the data quality refers to a methodical approach, policies, and processes within one organization that could they could manage the accuracy, validity, timeliness, completeness, uniqueness, and consistency of its data in the systems and the data flows. So data quality isn't some magic wand that could solve all the problems. So the problems should be resolved on a multiple layers. So first of all, they should resolve on approach. So this is a place where we can leverage a tool. It should be resolved on the internal policies and processes. So let's say the whole culture of one company goes to completely another level. So they all would be the data quality aware. Now we are going to go through data quality definition for one particular column as an example, and we will try to show all related things to the data quality through this one column. So we are going to look at the column date of birth from some table, and this particular column that we are looking is our subject of data quality, and it's called critical data element, and we are going to call her CDE from now. So the idea for every CDE, for critical data element, to try to ask ourselves, is this value that we are seeing, is it accurate? Is it valid? Is this value came on time? Is it complete? Is it unique across the whole data set? And is this consistent? So these 6 questions are actually data quality dimensions, and when we use them to check the quality of one particular CDE. So, and also what I want to say here is that we don't need to use all the dimensions. We should only focus on those dimensions that are of our interest for particular CDE and for particular data set. Going further, data quality dimension is some sort of feature or information that we're using to somehow quantify the quality of the data. So the first dimension is accuracy. So we're trying to understand how the data that we have accurately tries to represent the real world values. Some example of the poor accuracy is inconsistent spelling of product or person names, wrong addresses, etc. The second dimension is related to validity. So the data confers to the syntax, let's say format, type, of range of its definition. So for example, we have incorrect classification values for gender. Let's say we have woman, man, something third, fourth, but there are also some invalid values. Or let's say we have some customer type that should have a discrete values, but we have some other values that are not expected there. The third dimension is related to timeliness. So this can be shown. So this means how the change in real life reflects to our data. So for example, if a customer changes the address on July 1st and it's being updated on July 15th, so we have a 15 days of data inconsistency. The next dimension is completeness. So here we are going to check is our value that we have in the field complete or not. What does it mean? So let's say if we have a field that is called a phone number, inside our data set. And we expect that this phone number is the full phone number with the country code. However, for some phone numbers, we have only we have it without. This will mean even though we have populated field, it's not valid. The second dimension is uniqueness. So we saw this in a previous example with an email. We expect for some particular fields to be unique in the whole data set. And the last one is consistency, where this problem usually happens when we have one particular information spread across the different systems. Let's say we have a customer that closed his account. However, he has some orders on his system. So this is something that is not allowed. That is, we see one information on, let's say, one system of one organization, but in some other system, we see some different information. In order to use, so those dimensions were the tools that we can use in order to check the data quality for some particular CDE. And it depends of the data owners to define their own data quality rules. So data quality rules should be manually defined rules based on the dimension. So here in this particular example, date of birth, we define two different rules. One different rule is related to validity dimension, and it says the date of birth must be a valid date in a range from 1900 to current date. And the second one is related to completeness. So the date of birth must be entered for each individual. So that means that we don't allow empty fields. So once we have these data quality rules, we can use all of them and start working on the data quality. The data quality process consists on 4 steps. First, we need to define data quality requirements. Second one, we need to conduct data quality assessment. After that, resolve detected data quality issues, and finally monitor and control the data quality of a specific data set. So for the data quality requirements, we need, first of all, we need to understand our data. So for this data quality requirements, what we actually do, where we do data profiling, we do statistical analysis of our data set to understand the data, what we have inside, how many rows, how many distinct rows, etc., etc. Although some data quality problems can be discovered during data profiling, we don't do it in this step. The second step is related to data quality assessment. This is the place where we define data quality rules, the one that I mentioned previously. So here, based on our better understanding of the data sets, we define data quality rules for each columns, and we also define thresholds. Thresholds are how much of data inconsistency we can handle. So let's say for some CDEs, we would require very high thresholds, while for other less important, we could make a little higher tolerance. The third step is to resolve data quality issues, and this we do in 2 steps. First step is related to resolving the data quality issues in our data set to fix them. And the second thing is related to fix them on the source. So it's not good enough if we're talking about some data pipeline that is lending the data, let's say, to S3 or somewhere else or to some database. One thing is to fix them on the target, but completely another thing is to prevent for this poor data quality to even come to the target. And when this is done, The final step is to monitor and control our data sets. Why we need to do this? From very simple reason. Even though our data quality is fixed, it may happen that something will change somewhere and we will again have a bad data quality. And what we want to do with monitor, we want to know when this situation happens as soon as possible. So now let's go to one particular example, and let's try to leverage all the data quality process steps. So the first step here is to do data profiling. So data profiling for this particular column, date of birth, and as we mentioned, data profiling is just statistical information for our particular CDE. So from this CDE, we can see that, let's say, we have 8 records, we have 7 unique values, and we have 1 blank. So those are just the statistical information. We try to understand what this column means and what is the valid situation and what is invalid situation. Once we figure that out, we go to the second step, that is data quality assessment. Now we define 2 data quality roles. So we'll have a consistent example through all the slides. First role is validity. We already mentioned this one. The date should be in range between 1900 and current data. And the second one is completeness, so we don't allow the blanks. Once we define the role, we now run the data quality assessment, and we see that based on our roles, for validity we have a score of 75%, and for completeness we have a score for 88%. And this is very important. This is something that we call data quality scorecard. We will use this to continuously monitor the quality of our data during the time. So the main idea here is to improve the data quality, and with using this scorecard, this will be something similar as a KPI for our particular column or data set. So the third step here is to do the data issue resolution based on 2 steps. First step is to fix the existing data set. The second step would be to fix it fix the root cause that is causing these data quality issues. So fixing here would be very simple. On the first row, we would fix this invalid date. So here we can see that month and day replaced places, and to populate the date on the 5th row. And once we fix that, we are improving our data quality scorecard. So validity is ideally on 100% and completeness is on 100%. This is just one example that should get closer to the data quality itself. Of course, in a real production system with millions of rows, this would go a bit slower, but should show you how this process would look like. And once we fix the data set here, we are going to the source and trying to fix so we don't have these problems again. That would be it regarding the example. In order to have a good data quality, we can't do this by our own. We need to somehow leverage some tools so they can help us to speed up the process. And one tool for data quality should cover all 4 steps for the data quality. So it should cover data profiling, data assessment, scorecards, and issue resolution. So based on those criteria, we were investigating potential tools on the market, and we focus more on the open source solutions. And here we are just showing the list of let's say proven solutions. So all of those solutions, we are focusing on the big data, since since for the warehouses, the data quality is a bit simpler because all the sophisticated data warehouses already have some sort of embedded data quality tools and rules. And here we are just focusing on the big data. So all of those tools are relatively young because data quality in big data is something that is a buzzword for the last couple of years. And we see that their full implementation and full value will come in the following years. So from those specific tools, we selected one just to and we will give you a brief overview of this particular tool. And for this particular presentation, we pick up Soda. Why we pick up Soda? Because Soda is an open source tool. It's really good in terms of data reliability and observability, and it is also identified as a cool vendor for this year from Gartner. So regarding Soda, it is an open source. It has a lot of different connectors. The most important one is Soda SQL. We also need to mention that Soda support Spark and also Hive, Glue. So it's really simple to work with it. And this is that it has in its, let's say, open source version. So in order to work with Soda, it's really simple. The only thing we need to define is a warehouse file. Warehouse file is a file where we define connection. So we define host, port, the driver, database, and schema. And the second thing that we need is to define a scan file. Scan file is a YAML file where we define our test that we want to perform on top of the data. So here, what we need to define is the table that we want to monitor. And we need to define metrics and tests. So for metrics, there is a very rich portfolio of metrics that are defined out of the box from Soda. And I highly recommend you to visit Soda documentation for full list of metrics. So we could either use them, or sometimes when this is not enough, what we can do, we can write custom SQL queries where we could extract the particular information that we want to test, and we need to write the test on top of it. And of course, what we can also do, we can define tests for all the columns or for the specific columns that we want to test. And there is also extension of Soda that is called Soda Cloud. This part is paid. So inside Soda Cloud, there are some of the very interesting things that could make life of the developer easier in terms of data quality. So one thing is automatized monitoring. So based on the data that Soda Cloud receives, it can automatically detect some invalid situation and let's say send notification or perform some other action on top. It has team collaboration and some other fancy stuff that are coming with the cloud itself. One thing that I forgot to mention, when we perform data quality with Soda, as a result, we receive two, let's say, files or two results. One is measurements, and the second one is failed tests. So in measurements, we see all the statistics that we were performing, and in a failed test, we see the information for the particular columns that failed the test. And if it's integrated with the Soda, then those metrics are sent to the Soda Cloud. and we can see them in UI later on. That's all I had. Before we conclude, I want for you to emphasize few key takeaways. So first takeaway that we are seeing is that company have data quality issues. They may be aware, maybe they're not aware of these issues, but they don't care at the moment. This is something we see. Until they understand that this data quality issues directly impacts their business and hence the revenue. And this is the point when they starting to think about data quality. And this is the moment when the data quality projects are born. So once the data quality projects are born, this is the place when the whole development and play around with the data happens. And hopefully at the end, we will have a better data sets with a higher quality and hopefully continuous monitoring, so we can retain this data quality in a future. This is all I have. I see a couple of questions there. Let me stop sharing the screen. Let me go through the questions. Let's see. Okay, there is one question. In our account, we have data quality scorecards, great expectations. We have data updated over different time intervals, and we have a lot of downstream pipelines that run daily. Example, recommender search models that consume this data. Is there a systematic approach to estimate the impact of a specific data failure on downstream pipelines? For example, the impact of this failure is so high that we need to stop certain downstream pipelines and fix data issue first. So I would say this is something that, this is a really good question. This is something that is up to the, I would say, stakeholders to decide. So they need to decide how much impact this particular data brings, since they are the best, they are the main people who knows what is the data and how important is the data and how it impacts. For example, the one thing that I know that there is in SODA, so they can define different levels of thresholds based on the importance of the data quality. So they have generating either major or critical alerts levels based on the data. And of course, this is something that is again defined by the business. So I hope that I answered the question. If not, could you please give me a little bit more context?
Thank you very much for this answer, Milan. It's a really pressing problem for us these days because there are so many downstream pipelines, and in each of the downstream pipeline right now, we implement our own data quality checks. So essentially, if the data quality does not pass, we don't execute the next steps, and it's the red flag immediately to the support team. So everybody can start investigating on this issue. And but the problem of this approach is that there are so many downstream pipelines, and in each of them, there are different checks, and they're implemented in very different ways depending on the team. So yeah, that's kind of a pressing issue for us now.
Mm-hmm. So I understand your pain. This is something that very similar situation I have on my project. Accidentally, I also work with data quality right now. And the thing that we have is that we have different teams that are completely separated between each other. And sometimes they even use different tools to make the same thing. And similar is related to the data quality. And how we do it right now, since we are thinking that the company, let's say, lived with the poor data quality before. So we created one framework on top of the SODA, and we are enabled a couple of different flags. So each data owner can define whether he would like to fail the whole pipeline because of the bad data quality, or they want to pass it, but to receive a particular notification about the quality. For example, I am aware that my data quality is bad, but I would like to go with it, or this thing is crucial for me, please stop the whole pipeline, and it's better for me to work with all data than with the bad data. So it depends on the use case.
Thank you for sharing your experience. Thank you very much for your answer.
No problem. And there are a couple of more questions. Do we have any open source data management systems out there? So for the data management systems,
I was asking about master data management.
Master data management. I don't know by heart. This is something that I would need to check, and I can contact you directly.
Thank you.
And the second is from you again. Okay. If there are no more questions, thank you very much for your attention. Now I will.
I have one more question. Yeah, sorry for interruption. Yeah, for me it's like difficult to type. Yeah, because I'm like right hand in bandage. So I ask it. As far as I understand, all these tools they're like standalone. What about the cloud? For example, if a client has all the infrastructure in AWS, what is the best tool to integrate? For example, like probably in streaming or to process the S3 data.
Mm-hmm.
Do you have any recommendation? Yeah, what is the best tool to use in cloud?
We, for this, let's say, current project that I'm working, we had some investigation, prior investigation. There were a couple of options. One option was to write everything, the whole tool from scratch, to make the whole tool from scratch. Second option to stick somehow with an open source and to be cloud agnostic. And the third one is to leverage something from the AWS, if the client is using AWS. I'm not quite sure at this moment what was the idea, because it was a long time ago. The only thing that I remember is that there was some solution on AWS that could be leveraged, but the final decision was that it's not, let's say, mature enough. Not mature enough, but it didn't have as many options as the SODA had, and and the client was planned to leverage SODA Cloud as well as a long-term strategic.
Okay, for example, if we're talking about SODA, does it have LDAP solution to integrate with the client system?
Yes, it has. They are developing very rapidly, and we encountered on couple of, and they are very open-minded, and we encountered on couple of different things that we need from them. One of those things was LDAP, and they were just writing support, let's say, in a real time, and they provided us in a very next release. The same thing was, let me check. I think it was related to the Slack integration. So they didn't have it at the moment, and they provided this in the next release of Soda.
Yeah, okay, thank you.
No worries. All right. Thank you very much for your attention. Now I will pass the word to my colleague, Masha.
Thank you, Milan. I will start sharing my screen. Hi, please let me know if you can see it.
Yep.
Okay. So first, I'd like to say a few words about us. We are both big data engineers at Grid Dynamics. Luka is currently working at Inspire Brands, and I'm working at Nike. Now I'll start with a few general words about big data and data trends. Basically, the majority of successful businesses today operate online. Their consumers generate large volumes of data every second, and that data needs to be processed at high speed and also needs to generate results at equally high speed. This data can come from various sources such as sensors, devices, log files, web, and social media, much of it generated in real time and at very large scale. Analyzing this data provides insights that improve decisions and give confidence for making strategic business moves. Here on this graph, you can see the trends in the volume of data on a global level. The amount of data is increasing exponentially and is expected to reach 79 zettabytes by the end of the year. 1 zettabyte is equal to 1,000 exabytes. And the worldwide volume of data is expected to reach 180 zettabytes by 2025, which demonstrates the importance of the analysis of this data. The rapid and constant growth of data volumes caused the high popularity of big data technologies. Big data is currently one of the most in-demand niches in the development of enterprise software. Here you can see some of the most popular and current big data processing platforms, and I will highlight just a few of them. Starting with Apache Hadoop, it was a revolutionary solution for big data storage and processing at its time. And most of big data software is either built around or compliant with Hadoop. It is still a formidable batch processing tool that can be integrated with most other big data analytics frameworks. Its components, namely HDFS, MapReduce, and Yarn, are integral to the industry itself. Apache Spark is a newer open source framework created as a more advanced solution compared to Apache Hadoop, while Apache Flink is a robust big data processing framework for stream and batch processing. However, most of the tech giants haven't fully embraced Flink, but opted to invest in their own big data processing engines with similar features. For instance, we have Google's Dataflow and Apache Beam, and Twitter's Apache Heron. Meanwhile, Spark continues to have sizable support and backing. The idea behind today's talk is comparing two of the most prominent frameworks today, which are capable of both stream and batch processing, namely Spark and Flink. We will begin with Spark, and I will first give a theoretical overview of some of its key concepts and features. Apache Spark is an open source cluster computing framework that works very fast and is used for large-scale data processing. It is built around speed, ease of use, and sophisticated analytics, which has made it popular among enterprises in varied sectors. It was initially started at UC Berkeley in 2009 and open sourced in 2010. In 2013, the project was donated to the Apache Software Foundation, and in 2014, Spark became a top-level Apache project. In terms of architecture, at a fundamental level, an Apache Spark application consists of two main components: a driver, which takes the user's code and converts it into multiple tasks that can be distributed across worker nodes, and executors, which run on those nodes and execute the tasks assigned to them. Some form of cluster manager is necessary to mediate between the two. A key concept in Spark is the concept of RDDs, or resilient distributed datasets. An RDD represents an immutable collection of data that can be split across the computing clusters, leading to fast and scalable parallel computing. Another important concept is the concept of DAGs, or directed acyclic graphs, which is a logical flow of operations where nodes represent RDDs that contain the data and edges are operations to be applied on that data. In terms of speed, Spark owes its speed mostly to in-memory computing, as it is capable of processing tasks in memory and doesn't have to write back intermediate results to the disk. Spark is also capable of optimizing queries, which cuts down on execution time. In terms of flexibility, Spark supports multiple languages and allows developers to write applications in either Java, Scala, R, or Python. It also comes with the ability to run multiple workloads, including interactive queries, real-time analytics, machine learning, and graph processing. One application can combine multiple workloads seamlessly. When it comes to optimizing, Spark is capable of performing optimizations because it does not evaluate any transformation immediately. All transformations are lazily evaluated. They are added to the DAG, and the final results are available only when actions are called. This gives Spark the ability to make optimization decisions as all the transformations become visible to the engine. Spark uses two engines to optimize and run the queries, Catalyst and Tungsten in that order. What Catalyst does is it basically generates an optimized physical query plan from the logical query plan. It does this by applying a series of transformations like predicate pushdown, column pruning, and constant folding on a logical plan. This optimized query plan is then used by Tungsten to generate optimized code. Adaptive query execution improves the Catalyst optimizer by adjusting query plans based on runtime statistics that are collected during query execution. As of Spark 3.0, there are three major features in adaptive query execution, which include coalescing post-shuffle partitions, converting sort merge join to broadcast join, and skew join optimization. Caching or persistence is also available to users as an optimization technique by saving interim partial results so they can be reused in subsequent stages. In terms of fault tolerance, Spark is designed to handle worker node failures. It achieves this by using RDDs and lineage DAGs, as previously mentioned. A DAG contains the lineage of all the transformations and actions needed to complete a task. So in the event of a worker node failure, the same result can be achieved by rerunning the steps from the existing DAG. Spark Streaming uses write-ahead logs that store all the data received to log files in the checkpoint folder. Data is always written to the logs first so that Spark can recover even if it crashes before processing. Now a few words about deployment. Out of the box, Spark can run in a standalone cluster mode that simply requires the Apache Spark framework and the GAVM on each machine in the cluster. However, it's more likely you'll want to take advantage of a more robust resource or cluster management system. So you can use Hadoop Yarn, Apache Mesos, Kubernetes, or Docker Swarm. Now we will take a look at Flink. Apache Flink is an open source framework for stream and batch processing. It processes data quickly with high performance, stability, and accuracy on distributed systems. It provides low data latency and high fault tolerance. The significant feature of Flink is the ability to process data in real time. It started in 2010 when a group of German universities started a research project called Stratosphere. Flink started as a fork of Stratosphere's distributed execution engine, and Flink in German means quick or nimble. Later, in 2014, Flink became an Apache Incubator project, and later in that same year, it was accepted as an Apache top-level project. In terms of architecture, these are the building blocks of every Flink cluster. The Flink client takes the code of the Flink applications, transforms it into a job graph, and submits it to the job manager. The job manager distributes the work onto the task managers, where the actual operators, such as sources, transformations, and sinks, are running. Unified processing is the idea that Flink is heavily based on. Data naturally comes in streams, but when it's analyzed, it can be processed as either bounded or unbounded streams, and which of these paradigms you choose has very profound consequences. Batch processing is the paradigm where you process a bounded data stream. In this mode of operation, you can choose to ingest the entire data set before producing any results, which makes it possible to sort the data, compute global statistics, or produce a final report to summarize the whole input. Stream processing, on the other hand, involves unbounded data streams. Conceptually, at least, the input may never end, and so you're forced to continuously process the data as it arrives. Flink treats batch processing as a special case of streaming and has been aiming towards the unification of the two paradigms since its inception. In terms of flexibility, the Java API for Flink is by far the most mature and best supported, with Scala coming in as a close second. Other JVM languages, such as Kotlin, can be used but have no explicit support. And over the past several releases, Python support has been under active development, but is still behind the JVM languages. When it comes to deployment, Flink supports resource schedulers such as Yarn, Mesos, and Kubernetes, and the built-in Flink standalone scheduler also supports flexible deployment. When it comes to optimization, Flink leverages and extends Apache Calcite to perform sophisticated query optimization. This includes a series of rule and cost-based optimizations. The optimizer makes intelligent decisions based not only on the plan, but also on the rich statistics available from the data sources and fine-grained costs for each operator, such as I/O, CPU, network, and memory. Not all of the optimizations that Flink is capable of are enabled by default, so for some workloads, it is possible for users to improve performance by turning on some of these options. Flink's fault tolerance is based on preserving the state. The state that Flink manages is stored in a state backend, and there are two implementations of state backends that are available. One that stores the state in a database, which allows for storing state that is larger than the available memory, but it is approximately 10 times slower, and one that keeps the state in memory on the Java heap. Flink periodically takes persistent snapshots of the state in every operator and copies these snapshots somewhere more durable, such as a distributed file system. In the event of the failure, Flink can restore the complete state of the application and resume processing as though nothing had gone wrong. Now we will go on to the theoretical comparison and benchmarking. So in terms of stream processing, Flink is a clear winner when it comes to this, as it was created with stream in mind, while it was added later on to Spark. Here we can see that there's an important difference in how Spark and Flink process streams. Spark uses microbatches to emulate streaming, meaning it delivers near real-time processing. And for many use cases, Spark provides acceptable performance levels. Flink, on the other hand, offers true native streaming, meaning it processes each event in real time and provides very low latency. However, Spark 2.3 introduced a new low latency processing mode called continuous processing, which can achieve end-to-end latencies as low as 1 millisecond with at least once guarantees. However, it's still an experimental execution mode and is limited in the types of queries it supports. When it comes to memory management, until the creation of Tungsten, Spark mainly used the JVM's heap memory to manage all of its memory. Although it is a straightforward solution, it may suffer from overflow memory problems and the garbage collection pauses. Thanks to Tungsten, these problems started to disappear, and using data frames, Spark is now able to manage its own memory stack and to exploit the memory hierarchy, such as L1 and L2 CPU caches. Flink's designers, on the other hand, had this in consideration from the start. Flink maintains a self-controlled memory stack with its own type extraction and serialization strategy. The advantages of this approach are less memory errors, less garbage collection pressure, and a better space data representation, among others. When it comes to the community support, Spark has an excellent community background and is considered one of the most mature communities. Additionally, Spark has managed support, and it is very easy to find existing use cases with best practices which are shared by other users. In some cases, you can even find existing open source projects to use as a starting point. According to Stack Overflow, there are several times more questions about Spark than Flink. And another issue with Flink and Stack Overflow has to do with the often changing APIs of Flink, which means that many existing solutions become deprecated and unapplicable once a new version comes out. On the other hand, Flink is developing more and has more active contributors on GitHub. Iterative processing. Basically, iterative algorithms are present in many domains of data analysis, such as machine learning or graph analysis. With increasing interest to run these kinds of algorithms on very large data sets, there is a need to execute iterations in a massively parallel fashion. Flink programs implement iterative algorithms by defining a step function and embedding it into a special iteration operator. There are two variants of this operator, iterate and delta iterate. Both operators repeatedly invoke the step function on the current iteration state until a certain condition is reached. The iterate operator covers the simple form iterations where the step function consumes the entire input at each iteration. The delta iterate operator covers the case of incremental iterations. Incremental iterations selectively modify elements of their solution and evolve the solution rather than fully recomputed. Where applicable, this leads to more efficient algorithms because not every element in the solution set changes in each iteration. On the other hand, Spark doesn't really support any iterative processing operations. These operations must be implemented by developers and usually by using a regular loop statement. However, Spark does provide a cache operation, which lets applications cache a data set and access it from memory while doing iterative computations, which can help speed it up. When it comes to batch processing, Spark outperforms Flink, and basically it's due to the fact that Flink's stable API that supports batch processing is still evolving, while the data stream batch mode is in beta. Spark provides stable batch processing that is very unlikely to change with future versions. When it comes to optimization, both frameworks have mechanisms that analyze the code submitted by the user and yield the best pipeline code for a given execution graph. Spark also offers manual optimization, which allows the user to control partitioning and memory caching. When it comes to connectors, they both have a pretty wide array of connectors. However, Flink has no support for Bigtable, BigQuery, and has only JDBC support for AWS Redshift and Snowflake. When it comes to fault tolerance, there is no clear winner. Both systems are distributed and designed with fault tolerance in mind. This is all from me. Now my colleague will take over and share the results of our experiments.
Yeah, so that was that about the theoretical part. I'm going to tell you about our experience with Flink hands-on. So to start, we were performing our work on Amazon Cloud. We were using AWS EMR, the latest runtime, which is 6.4. It has, by default, a Flink 1.13 and Spark 3.1.2. Our cluster consisted of 11 nodes, which one was a master node and 10 worker nodes. All nodes were M5X large. As you can see, it's a machine with 4 filter cores, 16 gigabit memory, 64 EBS storage. We use a separate node, EC2 node, for Graphite and Grafana, where we stream the metrics. We stream the metrics using the native embedded classes like Grafana Sync for Spark and Grafana Reporter for Flink. The dataset is a public dataset that's used for a lot of benchmarks around the world. What we used is a catalog sales. It's a dataset about 900 gigabytes and customers with 4 gigabytes. And we can move on to benchmarking. So here you can see our results. So the first one is the filter. It was a simple job that filters the quantity of the sale module 2. Why we did that? It was because it will filter around 50% of the result set. That's why it took the longest, because it had most time spent writing back to S3. Join was done between sale and customers on customer's key. And aggregation was a simple aggregation of revenue per day. Keep in mind that the Flink part was done using the data stream API in batch mode. So that's why Flink is slower, as we can see, just because it's an experimental and new way of Flink, where they have the same API for stream and batch. So we can go on the next slide. So yeah, like we saw, Spike execution time was on average shorter than Flink for batch processing. And as I said, that's because we use the unified sync, which is completely new. And for stream benchmarking, our architecture consisted of Kinesis to Kinesis aggregation. We have Amazon Kinesis as a source, Amazon EMR, which had Spark or Flink job on it, and that did aggregation and wrote to Amazon Kinesis. Checkpointing was performed on S3. For this one, we used a different data set. We created our own messages, where what we did was basically aggregation and counting the suspicious messages. Here we can see a lot higher throughput with Flink. Although with only filtering job, Flink was only 30% faster. Here we have to keep in mind that Flink has a native support to Kinesis, whereas Spark does not anymore. So Spark is using the Kubole library. And for some conclusion, which is on, yeah. So let's start with the difficulties for Flink. As Masha said, the two of us, we mainly do our job in Python, and we wanted to start to do Flink in Python also. But because of a lack of documentation, we had to move to Scala. And even though the ratio of Spark and Flink questions on Stack Overflow is not that large, most of the Flink questions are updated because the API is changing and they're constantly moving towards a different direction. So that's why even if you find your question, most of the time the answer will be deprecated. But even though with the bad side, Flink is much better at streaming and it has a lot higher throughput and much lower latencies. Whereas, as we saw, Spark performed a lot better in batching. Spark has a large positive side, which is ease of development. Everything out of the box, mostly everything out of the box works. So deployment to EMR and starting the job is pretty straightforward. Whereas for Flink, you cannot have your job on S3. You have to copy it to the cluster, of course. We had a lot of problems along the way. Let's say Flink didn't have permissions to write logs on the clusters. So we had to create a script before starting a job to give the permission to Flink. Also, Flink, for some reason, we had to make a workaround and put S3 access keys in the Flink configuration files because it didn't integrate well with IAM roles, which for Spark worked out of the box. Also, the libraries, the S3 libraries that are provided by EMR in this latest version are actually deployed in the bad folder. So you have to move them around a bit before starting a job. And I think that was all. If you have any questions, I think that this will be the time. Yeah, so there is one question from Simon. Having compared also compilation time and deployment time, for example, how much time is needed to make the job starting once deployed? Yeah, so we actually aggregated all those metrics, but they aren't in presentation and we really haven't analyzed them already. So they will be in the blog, and once we make it, I'll make sure to notify you. So another question is, I need to create a data pipeline quickly. Which framework should I use? Well, definitely Spark, since out of the box, everything is working. And for us, and I think Masha agrees with me, the learning curve is a lot easier. Also, you can have programmers really quickly start working in Python, which is not the case for Flink. Join filters, etc., were performed on key fields in the stream and batch. Yes. Can you tell about differences in configuration for jobs between Spark and Flink? Because Spark has a really powerful way of configuration. Yeah, that part was actually, we dedicated a lot more time to try to tweak Flink jobs in order to make it more competitive in batches. Since Flink jobs have only parallelism and number of task slots per task manager. So for Spark, we use the simple configuration of just using the executor memory and number of executors per cluster. Simon, did you consider to make comparisons using both native languages and Python? That wasn't part of our scope for now, but maybe in some future, because for now we stick with Scala. As I told, the documentation for Python is really bad from our experience, and it was hard to learn Flink from scratch using Python. And here's one more. Why did you say to test filter, join, and group by only? But that was simply because that are the building blocks of everyday jobs in the industry, the ones that are most important, and the ones that they're just the building blocks of every job.
I would like to add here that for more detailed testing, it will probably be a good idea to implement more complicated jobs than what we used here.
And also we are going to test, our scope was to also test on Kafka, because it really, Kinesis really gives an advantage to Flink. So once we do that, it will be also in the blog. Have you ever seen Flink in production? If so, for which purposes it was used? No, this was our first time learning Flink from the scratch, so we never use it on the project, but maybe someone here actually used. I think that's the next question also. So yeah, we don't use Flink on projects we are on. How is the learning curve for Flink in your opinion? I feel like at least for Scala, it heavily relies on Scala practices. But the biggest problem is basically the documentation. Most of our time we were digging through Java class definitions and learning like that. Why did you mark Spark Streaming X? I'm not sure what you mean. Do you have a sandbox available to try Flink? Once we finish the blog, we'll push all the code to Git with step-by-step deployment, how to deploy it to EMR. What about UDFs and native functions? Well, I'm not sure what you mean, but from the perspective of Windows, what you can do in Windows, Flink is a lot more, has a lot more options, but forces you to implement those from what we saw. So Flink window aggregations are much more powerful than Spark. You measurement time, what about resources? Oh, we measured the CPU time and it was, for batch mode, it was pretty much the same. But detailed analysis about memory on and off heap, we'll have to wait because we have all those graphs saved, but we didn't have time to analyze it yet. It will be discussed in the blog more details. Does Flink SQL really work? If you mean by table API, it still works, but they are forcing the data stream API to be used more and more. Yeah, it works. It's a part of table API. So yeah, you can do the same stuff as in Spark as well. We didn't, okay. We didn't actually perform benchmarking for table API, but we are still thinking on whether to do that. We haven't checked the data catalog. Maybe will be considered in the future. Also, what we considered is making the same tests, just with different state backends. I hope, Simon, you're writing a message because we are still waiting for it. The last question. Yeah, so we tried Parquet. And we are yet to do Avro and JSON. But we haven't got all the metrics for those yet. But we planned only on doing Avro and Parquet, not JSON for now. does Flink support Apache Berg? To be honest, I have to check that out. I'm not sure at the moment. I know that, for example, Flink cannot read or write to Azure Data Lakes, which is disappointment. And here's Simon to the rescue, so that's not. So if nobody has any more questions, I think we are done here.
Thank you very much, Luka. Let's wrap it up. Thank you very much for your attentions. I will wish you a nice rest of the day. Bye-bye.
Thank you. Bye.